Welcome back. In this lab, we're going to do two experiments. But first, let's quickly review our setup. So here is our motor over here, and the motor has an angle encoder attached to it. And this encoder is going to send signals to Arduino about what the disk angle is. The Arduino is going to differentiate that angle to calculate the speed. And based on the speed or otherwise, it can prescribe a voltage. So Arduino is going to give a signal to the DAC over here, the digital to analog converter, which is going to give the signal to the motor controller board over here. Motor controller board is going to provide a fraction of the 24-volt supply to the motor through these wires over here. Okay. Now let me share my screen to go over the two experiments. So this right here is the equation involving the voltage and the speed of the motor. So you're given the voltage VA, and then the motor moves with the speed omega governed by this differential equation. There is a constant term over here, which makes this equation technically not linear, but we can easily get rid of it by defining the difference of the two as the actual voltage needed to move the motor, because this constant term is the voltage required to just barely move the motor. Okay, so if you define the actual voltage minus this minimum voltage as the real voltage, which or the actuating voltage we give to the motor, then we can rearrange this or rewrite this first order differential equation in this standard format, where KDC is the DC gain of the system and tau is a time constant of the system. And similarly, we can get a transfer function KDC over tau s plus 1 from it. Now, we had we had to find the differential equation or the transfer function. And for that, we have done two approaches. One, we individually measure the constants like RA, the resistance, KT and KE, the motor constants, and the back EMF constant, and things like that. And we put together a transfer function. So that was approach one. The second approach is that you give, it's an experimental approach, that you give a constant input to the system, a constant voltage to the system. And by looking at the motor speed, we can tell what the transfer function is. So for example, that if you have this motor over here with the transfer function, then let's say you give a constant voltage. This is the V, which is over and above the minimum voltage. So let's say you give a constant V of X to the motor, then the speed of the motor is going to start from 0 and ultimately reach a steady state speed. And this steady state speed is equal to DC gain multiplied by the input voltage X that you give. So by measuring the voltage you give and the steady state speed, you can calculate the DC gain. And the time taken to reach about 63.2% of this steady state speed, that is your time constant. And by measuring that from the graph, you can get the time constant. So this was an experimental way of finding the transfer function, and we did that before. But there is one more experimental way of doing everything, finding the transfer function, that is, and that is, instead of giving the constant voltage, i.e. step inputs, we can give sinusoidal voltage. So if you give a sinusoidal voltage input to the motor speed eventually is going to have a sinusoidal behavior of the same frequency, but different amplitude and a different phase. And if you plot this amplitude change and the phase change as a function of the different frequencies of sinusoids you give to the motor, you get what we call as a body plot. And by looking at the body plot, we can infer what the transfer function is. So that's a very common system identification way. And then we can use that to further see whether a transfer function is correct or not. So that would be our experiment one. Experiment two is to actually start designing controllers, and we're going to try the simplest controller, and that's a proportional controller. So according to proportional controller, the voltage VA minus VA min that you give to the motor is proportional to how far you are away from the desired speed. Let's say the desired speed omega d is 12. So we're going to measure the actual speed using Arduino. And inside the Arduino code, we're going to do the difference between 12 and the actual speed. And proportional to that, we provide the voltage to the motor. So we'll analyze the behavior of this proportional controller also in this lab. And that would be our experiment number two.